Too many unanswered questions?
I agree. And then, of course, we have chapter 4, this black hole at the beginning of time.
Space-time singularity.
Indeed.
Imagine questions that have troubled the greatest minds for centuries. Mysteries that stretch our understanding of space, time, and existence itself. These are some of the biggest questions that keep astrophysicists up at night. Let's unravel these mysteries one by one. Planets, stars, galaxies, everything visible comprises less than 5% of the universe. The rest? It's dominated by entities known as dark matter and dark energy, which make up about 25% and 70% of the universe, respectively. Dark matter is unlike anything we can see or touch. It doesn't emit, absorb, or reflect light. Its presence is inferred from the gravitational effects it has on visible matter. Without dark matter, galaxies would fling apart. The gravitational pull from visible matter alone isn't sufficient to hold them together. This invisible substance exerts a gravitational force, thereby shaping the structure of the universe. We detect the existence of dark matter through its gravitational influence on light, bending it. This bending, known as gravitational lensing, acts as a cosmic magnifying glass, revealing the presence of this dark substance. Although we can't see dark matter directly, its interaction with gravity confirms its existence, and it is there in vast amounts. Dark energy, on the other hand, is even more elusive. Its effects are visible in the universe's accelerated expansion. In 1929, Edwin Hubble discovered that distant galaxies were receding faster than nearer ones, a phenomenon evident from the redshift in their light. This expansion isn't slowing down as previously thought, it's speeding up, driven by dark energy. This mysterious force, making up most of the universe, acts contrary to gravity and is intrinsic to space itself. The more space expands, the stronger dark energy becomes. It's as if this energy is a property of space, not a physical substance, continuously generating more space. While we have several hypotheses about dark matter and dark energy, from exotic particles to a property of space itself, no theory yet fully explains their nature. This frontier of science, while understandably frustrating, marks the limits of our current knowledge. As we explore these uncharted cosmic territories, these mysteries indicate just how much we have yet to learn, reminding us that we are merely at the beginning stages of exploring the immense cosmic ocean. In our universe, the most unassuming substances often hold the keys to the biggest mysteries. Among these, antimatter isn't just a mysterious substance used in science fiction movies. It represents one of the most baffling puzzles in physics. Why does anything exist at all? For every particle that exists, there is an antiparticle. Its mirror opposite in charge and spin, but identical in every other way. Electrons have positrons. Protons have antiprotons. When matter and antimatter meet, they annihilate each other, releasing pure energy in the form of photons and leaving nothing behind. If this perfect symmetry prevailed, the universe should have self-destructed moments after the Big Bang, leaving nothing but light. Yet our very presence confirms that didn't happen. Matter exists, we can touch it, see it, and live in it. This leads to an inevitable question. Why is there more matter than antimatter? This imbalance, known as the matter-antimatter asymmetry problem, suggests that during the universe's inception, conditions favored the production of matter slightly more than antimatter. For every billion pairs of particles and antiparticles that annihilated each other, one particle of matter was left unpaired, leading to the universe as we know it. This slight favoritism implies a fundamental asymmetry in the laws of physics, particularly in how the universe treats matter versus antimatter. The standard model of particle physics, though incredibly successful, does not account for this asymmetry. Experiments like those conducted at CERN with the ALPHA experiment and the ALINA facility aim to trap antihydrogen and compare its behavior to hydrogen. By measuring how antihydrogen atoms respond to gravitational fields and testing their spectral lines with unprecedented precision, scientists probe the very foundations of modern physics. They are not just testing properties of antimatter, but the underlying symmetries of space and time themselves. Our current models of physics are incomplete. They falter at fully explaining why the universe prefers matter to antimatter, why we exist, and why there is something rather than nothing. The observable universe, spanning 46 billion light-years in all directions, is just the beginning. Beyond this cosmic boundary lies the unobservable universe, which might be infinitely larger and utterly unseeable due to the limits of light and time. Here's what could lie beyond. The universe may extend endlessly, filled with a potentially infinite number of galaxies. This infinite space could mirror the part we can see, with matter repeating across a boundless space, creating an eternal pattern of galaxy clusters and voids. Alternatively, if the universe curves back on itself like a higher dimensional sphere, traveling far enough in one direction might eventually bring you back to your starting point. This closed universe suggests a cosmos that is both finite and borderless. As the universe expands, accelerated by dark energy, it stretches space itself, causing galaxies to recede faster than light can travel. This expansion not only seals off the far reaches of the cosmos, but also ensures that they remain forever hidden from us. What lies beyond is likely an extensive, possibly infinite stretch of galaxies, star systems, and phenomena that could drastically differ from the physics we know. Black holes, regions where gravity is so intense that nothing can escape, are some of the most fascinating objects in the universe. The center of a black hole, known as the singularity, is where the known laws of physics cease to function due to infinite density and gravity. The journey into a black hole passes through the event horizon, the ultimate point of no return. Beyond this, all theories become speculative, but general relativity suggests that space and time swap roles. Inside this boundary, all paths lead inevitably to the singularity, a point where traditional dimensions of space and time collapse entirely. At the singularity, density and gravity reach their peak, theorized as infinite. The crushing forces are unimaginable and would disintegrate any physical matter daring to approach. Here, the equations of physics as we know them break down. We understand that at this core, the curvature of spacetime becomes infinite, and all mass is crushed into an infinitely small point. Describing a black hole might seem simple, as they are defined by just three properties: mass, charge, and angular momentum. However, the conundrum known as the black hole information paradox arises because, according to quantum mechanics, information cannot be lost. This paradox marks a fundamental clash between general relativity and quantum theory, as information falling into a black hole appears to vanish, contradicting quantum principles. Venturing beyond the event horizon theoretically leads to some of the most bizarre realities. Some theories propose that black holes could be gateways to other parts of the universe or different universes entirely, a concept often depicted through the idea of a wormhole. However, such scenarios venture into the realm of speculative physics with no empirical evidence yet. In essence, the center of a black hole remains a place of intense theoretical interest and extreme physical conditions. It represents one of the most extreme environments in the universe, where the known laws of physics are not just broken, but shattered. As we strive to understand the forces at play within these monstrous objects, black holes continue to challenge our understanding of the fundamental fabric of reality. The genesis of everything we know begins with the Big Bang, a monumental burst of reality as we understand it, where time, space, and matter were all conceived in a singular, defining moment. Despite its name, the Big Bang wasn't an explosion in space, but rather an expansion of space itself. At the instant of this event, the universe was infinitesimally small, hot, and dense. From this fiery beginning, the universe stretched and cooled, laying down the fundamental structures of stars and galaxies we observe today. Despite the latest findings from the James Webb Space Telescope, the evidence supporting the Big Bang as the origin of our universe remains unshakable. The Big Bang posits that the universe started as a point, or singularity, and has been expanding ever since. As it expanded, it cooled, transitioning from a state of incomprehensible heat, where particles and antiparticles spawned and were annihilated quickly. This era saw the universe's temperature drop sufficiently for quarks to come together, forming protons and neutrons, which then gave rise to atoms. Most of the universe's matter was created during this time, matter that builds everything from stars to planets to humans. An important discovery that provides a snapshot of the infant universe is the cosmic microwave background radiation, a thermal remnant from the time atoms first formed about 380,000 years after the Big Bang. This relic radiation is what remains of that primal heat, with a panoramic image of the universe at its birth. The Big Bang theory offers a robust explanation for the observable universe's origins, yet it also introduces profound mysteries. What preceded the Big Bang? Is our universe unique, or merely one of many in an infinite multiverse? These questions challenge our understanding of natural laws, suggesting the universe's origins and ultimate fate might be bound by frameworks and theories yet to be discovered. As we continue to explore these cosmic mysteries, we find ourselves peering not just into space, but also back in time, drawing ever closer to that primordial moment of creation. Yet the more we learn, the more it seems the universe guards its secrets. Perhaps the ultimate question remains just out of reach. Are we indeed the universe questioning its own existence?